What if I told you that the energy that powers your phone, the process that creates chlorine for your pool, and even the way your brain talks to your hand are all connected by one incredible field of science? Welcome back to the channel. Today, we're diving into the fascinating world of electrochemistry. Let us begin with the Daniell cell, which is the simplest example of a galvanic cell. In this cell, zinc metal reacts with copper ions in solution. Zinc gets oxidized to zinc ions, copper ions get reduced to copper metal, and this redox reaction releases chemical energy. The key idea is that this chemical energy is converted directly into electrical energy. When the concentrations of zinc ions and copper ions are both 1 molar, the Daniell cell produces a potential difference of exactly 1.1 volts. Any device that converts chemical energy into electrical energy in this way is called a galvanic cell or a voltaic cell. Now, consider what happens if we apply an external voltage opposite to the cell's own potential. As this opposing voltage is slowly increased, the cell continues to function normally until the external voltage becomes equal to 1.1 volts. At this point, the reaction completely stops and no current flows through the circuit. If the external voltage is increased beyond 1.1 volts, the direction of the reaction reverses. The cell now uses electrical energy to force a non-spontaneous chemical reaction. In this mode, the same setup behaves as an electrolytic cell. This simple example clearly shows the difference between galvanic cells, which produce electricity, and electrolytic cells, which consume electricity. A galvanic cell is an electrochemical device that converts the chemical energy of a spontaneous redox reaction into electrical energy. In simple terms, the energy released during a redox reaction is transformed into electrical work, which can then be used to run devices like motors, heaters, fans, or any electrical gadget. The Daniell cell is a classic example of such a galvanic cell. In this cell, zinc metal reacts with copper ions in solution to form zinc ions and copper metal. This overall reaction is actually a combination of two half reactions. At one electrode, copper ions gain electrons and get reduced to copper metal. At the other electrode, zinc metal loses electrons and gets oxidized to zinc ions. These two half reactions occur in different regions of the cell called half cells or redox couples. The copper electrode, where reduction occurs, is called the reduction half cell, while the zinc electrode, where oxidation occurs, is called the oxidation half cell. On the same pattern as the Daniell cell, we can construct many galvanic cells by combining different half cells. Each half cell consists of a metallic electrode dipped into a solution containing its ions. Externally, the two half cells are connected by a metallic wire through a voltmeter and a switch, while internally, their solutions are connected by a salt bridge. In some special cases, both electrodes dip into the same electrolyte, and then a salt bridge is not required. At the interface between an electrode and its electrolyte, two opposite processes tend to occur simultaneously. Metal ions from the solution may deposit on the electrode, making it positively charged, while metal atoms from the electrode may enter the solution as ions, leaving electrons behind and making the electrode negatively charged. When equilibrium is established, this separation of charge creates a potential difference between the electrode and the solution. This potential difference is called the electrode potential. When all species in half cell are present in unit concentration, the electrode potential is known as the standard electrode potential. According to IUPAC convention, these are expressed as standard reduction potentials. In a galvanic cell, the half cell where oxidation takes place is called the anode, and it has a negative potential with respect to the solution. The half cell where reduction takes place is called the cathode, and it has a positive potential with respect to the solution. Due to this potential difference, when the switch is closed, electrons flow from the negative electrode to the positive electrode. The direction of conventional current is opposite to the direction of electron flow. The potential difference between the two electrodes of a galvanic cell is called the cell potential and is measured in volts. When no current is drawn from the cell, this potential difference is known as the electromotive force, or EMF, of the cell. By convention, the anode is written on the left and the cathode on the right while representing a galvanic cell. Under this convention, the cell potential is given by the electrode potential of the right-hand half cell minus that of the left-hand half cell. For example, consider a cell in which copper reacts with silver ions. Silver ions get reduced at the cathode, while copper metal gets oxidized at the anode. The cell is represented with copper on the left and silver on the right, and the cell potential is calculated as the standard electrode potential of silver minus that of copper. It is important to note that the potential of an individual half cell cannot be measured directly. Only the potential difference between two half cells can be measured. To solve this problem, one reference half cell is chosen, whose potential is defined as 0. This is the standard hydrogen electrode. It consists of a platinum electrode coated with platinum black, dipped in an acidic solution with hydrogen gas bubbled through it at 1 bar pressure. The concentration of hydrogen ions is maintained at 1 molar. Under these standard conditions, the electrode potential of the hydrogen electrode is taken as 0 at all temperatures. When the standard hydrogen electrode is connected to another half cell, the measured EMF of the cell gives the standard electrode potential of the other half cell. For example, when connected to a copper half cell under standard conditions, the measured EMF is plus 0.34 volts, which is the standard electrode potential of copper. When it is connected to a zinc half cell, the measured EMF is minus 0.76 volts, which is the standard electrode potential of zinc. A positive standard electrode potential indicates that the species gets reduced more easily than hydrogen ions, while a negative value indicates that hydrogen ions can oxidize the species. This explains why copper does not dissolve in hydrochloric acid, but zinc does. Using these values, the EMF of the Daniell cell can be calculated by subtracting the standard electrode potential of zinc from that of copper, giving a value of 1.10 volts. Sometimes, inert electrodes such as platinum or gold are used. These electrodes do not participate in the reaction, but simply provide a surface for oxidation or reduction and allow the flow of electrons. Examples include the hydrogen electrode and the bromine electrode. Standard electrode potentials are extremely important because they help us compare oxidizing and reducing strengths. Only after that can the Nernst equation be written correctly using the reaction quotient. In general, for any electrochemical reaction, the Nernst equation relates the cell potential to the standard cell potential and the reaction quotient, which contains the concentrations of products raised to their stoichiometric powers divided by the concentrations of reactants raised to theirs. Now let us connect this to chemical equilibrium. In a Daniell cell, as the circuit remains closed, zinc ions keep forming and copper ions keep getting consumed. As a result, the cell potential gradually decreases. Eventually, a point is reached where the voltmeter shows 0 potential. At this stage, no net reaction occurs and the system has reached equilibrium. Under equilibrium conditions, the cell potential becomes 0 and the Nernst equation reduces to a direct relationship between the standard cell potential and the equilibrium constant of the reaction. At 298 Kelvin, this relationship becomes a very simple logarithmic equation. This is extremely powerful because it allows us to calculate equilibrium constants for reactions that are otherwise difficult to measure experimentally. A large value of the equilibrium constant means the reaction is highly spontaneous in the forward direction, which corresponds to a large positive standard cell potential. Next, let us relate electrochemistry to thermodynamics. The electrical work done by a galvanic cell is equal to the product of the cell potential and the charge passed. When the cell operates reversibly, the maximum electrical work obtained is equal to the decrease in Gibbs free energy of the reaction. This leads to one of the most important equations in electrochemistry. The change in Gibbs free energy is equal to minus NF multiplied by the cell potential. Here, the cell potential is an intensive property, meaning it does not depend on the amount of substance, while Gibbs free energy is an extensive property and depends on the number of electrons transferred. That is why doubling the reaction doubles the change in Gibbs energy, but does not change the cell potential. Under standard conditions, this relationship becomes even more useful. The standard Gibbs free energy change of a reaction is directly related to the standard cell potential. From this value, we can again calculate the equilibrium constant using thermodynamic relations. This beautifully closes the loop between electrochemistry, equilibrium, and thermodynamics, showing that all three describe the same underlying chemical reality from different angles. Before studying how electricity flows through electrolyte solutions, we must clearly understand a few basic terms. Electrical resistance, represented by R, is the opposition offered by a material to the flow of current. It depends directly on the length of the conductor and inversely on its cross-sectional area. The proportionality constant involved here is called resistivity. Resistivity is a characteristic property of a material and represents the resistance of a conductor that is 1 meter long with a cross-sectional area of 1 square meter. Lower resistivity means easier flow of current. The reciprocal of resistance is called conductance. Its SI unit is Siemens. Similarly, the reciprocal of resistivity is called conductivity. Conductivity tells us how well a material conducts electricity and is expressed in Siemens per meter. A high value of conductivity indicates good conduction, while a low value indicates poor conduction. The conductivity of materials varies over a very wide range. Metals such as copper, silver, and gold have very high conductivity and are known as conductors. Materials like glass and Teflon have extremely low conductivity and are called insulators. Substances whose conductivity lies between conductors and insulators are known as semiconductors. An interesting special case is superconductors, which have zero resistivity at very low temperatures. In metals, electrical conduction occurs due to the movement of electrons and is called electronic or metallic conduction. In electrolyte solutions, conduction occurs due to the movement of ions and is called electrolytic or ionic conduction. Even pure water conducts electricity slightly because it contains a small concentration of hydrogen and hydroxide ions. When electrolytes are dissolved in water, they produce ions and therefore significantly increase the conductivity of the solution. The conductivity of an electrolyte solution depends on several factors, such as the nature of the electrolyte, the size and mobility of ions, the solvent, concentration, and temperature. Unlike metals, the conductivity of electrolyte solutions increases with increase in temperature because ion mobility increases. To measure the conductivity of ionic solutions, we cannot use direct current because it changes the composition of the solution. Therefore, alternating current is used along with a specially designed conductivity cell. This cell contains 2 platinum electrodes coated with platinum black. The resistance of the solution between these electrodes depends on the distance between them and their area. The ratio of distance to area is called the cell constant. Since measuring distance and area accurately is difficult, the cell constant is determined using a solution of known conductivity, usually potassium chloride. Once the cell constant is known, the conductivity of any solution can be calculated easily by measuring its resistance. Modern conductivity meters perform these measurements directly, making the process faster and more accurate. However, conductivity alone is not sufficient to compare different electrolytes because it depends on concentration. To overcome this limitation, we define a more meaningful quantity called molar conductivity. Molar conductivity is the conductivity of a solution containing 1 mole of electrolyte, and it increases as the solution is diluted. This happens because dilution increases the volume containing 1 mole and reduces interionic attraction. While conductivity always decreases on dilution, molar conductivity always increases. When the concentration approaches 0, molar conductivity reaches a maximum value, called limiting molar conductivity. For strong electrolytes like sodium chloride or potassium chloride, molar conductivity increases slowly with dilution. A plot of molar conductivity against the square root of concentration gives a straight line. Extrapolating this line to 0 concentration gives the limiting molar conductivity. Kohlrausch studied the limiting molar conductivities of strong electrolytes and observed that each ion contributes independently to the total molar conductivity. This observation is known as Kohlrausch's law of independent migration of ions. According to this law, the limiting molar conductivity of an electrolyte is equal to the sum of the limiting molar conductivities of its constituent ions. This law is extremely useful, especially for weak electrolytes. Weak electrolytes like acetic acid do not dissociate completely at higher concentrations, so their limiting molar conductivity cannot be calculated directly by extrapolation. Instead, Kohlrausch's law is used to calculate their limiting molar conductivity from the known values of strong electrolytes. Once the limiting molar conductivity of a weak electrolyte is known, we can calculate its degree of dissociation at any concentration. From the degree of dissociation, the dissociation constant of the weak electrolyte can be determined. Thus, conductivity measurements provide a powerful method to study ionic equilibria in solution. In an electrolytic cell, an external source of electricity is used to force a chemical reaction that would not occur on its own. These electrochemical processes are extremely important both in laboratories and in large-scale chemical industries. One of the simplest electrolytic cells consists of 2 copper strips dipped in an aqueous solution of copper sulfate. When a direct current is passed through the cell, copper ions from the solution move towards the cathode, which is the negatively charged electrode. At the cathode, copper ions gain electrons and get reduced to copper metal, which gets deposited on the electrode. At the same time, the copper anode loses electrons and dissolves into the solution as copper ions. Thus, oxidation takes place at the anode and reduction takes place at the cathode. Overall, copper is simply transferred from the anode to the cathode. This principle is used industrially for the purification of copper. Impure copper is made the anode, and pure copper is used as the cathode. On passing current, pure copper gets deposited on the cathode, while impurities either remain in the solution or settle as anode mud. Electrolysis is also the only practical method to produce highly reactive metals like sodium, magnesium, and aluminum, because no suitable chemical reducing agents are available for them. Sodium and magnesium are obtained by electrolysis of their molten chlorides, while aluminum is produced by electrolyzing aluminum oxide dissolved in molten cryolite. Now let us look at the quantitative aspects of electrolysis. Michael Faraday studied the relationship between electricity and chemical change and proposed 2 important laws. According to Faraday's first law, the amount of substance deposited or liberated at an electrode is directly proportional to the quantity of electricity passed through the electrolyte. Faraday's second law states that when the same quantity of electricity is passed through different electrolytes, the amounts of substances liberated are proportional to their equivalent weights. The quantity of electricity passed through a circuit is given by the product of current and time. The charge carried by 1 mole of electrons is a constant called Faraday, represented by F, and its value is approximately 96,500 coulombs per mole. This means that reactions involving more electrons require more charge. For example, 1 mole of silver ions needs 1 Faraday of charge to get reduced, whereas 1 mole of magnesium ions requires 2 Faradays, and aluminium ions require 3 Faradays. Using Faraday's laws, we can calculate the mass of a substance deposited during electrolysis if the current and time are known. This forms the basis of all numerical problems related to electrolysis in exams. Finally, the products of electrolysis depend on 2 main factors: the nature of the electrolyte and the type of electrodes used. If inert electrodes like platinum are used, they do not take part in the reaction. If reactive electrodes are used, they may dissolve or participate in the process. In aqueous solutions, multiple species are present, including water, so there is competition between possible reactions. The reaction that actually occurs depends on standard electrode potentials and also on overpotential effects. For example, during the electrolysis of molten sodium chloride, sodium metal is obtained at the cathode and chlorine gas at the anode. But during the electrolysis of aqueous sodium chloride, hydrogen gas is produced at the cathode instead of sodium because hydrogen ion reduction is more favorable. At the anode, chlorine gas is produced instead of oxygen due to the overpotential of oxygen evolution. Similarly, in sulfuric acid, oxygen is evolved at lower concentrations, while at higher concentrations, different oxidation products may form. This shows that electrolysis is controlled not just by thermodynamics but also by kinetics and experimental conditions, making it a powerful yet subtle process in electrochemistry. Any cell or battery that we use as a source of electrical energy is essentially a galvanic cell. In these devices, the chemical energy released during a redox reaction is converted directly into electrical energy. For a battery to be practically useful, it should be light, compact, and capable of supplying a nearly constant voltage during its operation. Based on their reusability, batteries are broadly classified into primary and secondary batteries. Primary batteries are those in which the chemical reaction occurs only once. After the reactants are consumed, the battery becomes dead and cannot be recharged. The most common example is the dry cell, also known as the Leclanché cell, which is widely used in devices like clocks, remotes, and radios. In a dry cell, the zinc container itself acts as the anode, while a carbon rod surrounded by manganese dioxide acts as the cathode. The electrolyte is a moist paste of ammonium chloride and zinc chloride. During operation, zinc undergoes oxidation at the anode, releasing electrons, while manganese dioxide is reduced at the cathode. The oxidation state of manganese decreases from +4 to +3. Ammonia formed in the reaction combines with zinc ions to form a complex, helping the reaction to proceed smoothly. A dry cell provides a potential of about 1.5 volts. Another important primary battery is the mercury cell, which is used in low-current devices such as hearing aids and watches. In this cell, zinc-mercury amalgam acts as the anode and mercury oxide mixed with carbon acts as the cathode. The electrolyte is an alkaline paste of potassium hydroxide and zinc oxide. During discharge, zinc is oxidized and mercury oxide is reduced to liquid mercury. One major advantage of the mercury cell is that its voltage remains almost constant throughout its life, around 1.35 volts, because no ions from the electrolyte are consumed or produced in the overall reaction. Secondary batteries are rechargeable batteries. After use, they can be recharged by passing an electric current in the opposite direction, which reverses the chemical reactions. A good secondary battery can undergo many charging and discharging cycles. The most important secondary battery is the lead storage battery, commonly used in automobiles and inverters. It consists of a lead anode and a cathode made of lead dioxide, with sulfuric acid acting as the electrolyte. During discharge, both the electrodes are converted into lead sulfate and water is formed. As the battery discharges, the concentration of sulfuric acid decreases. When the battery is recharged, the reactions reverse, converting lead sulfate back into lead and lead dioxide. Another secondary battery is the nickel-cadmium cell. It has a longer life and better durability than the lead storage battery, but is more expensive. In this cell, cadmium acts as the anode and nickel hydroxide acts as the cathode, with an alkaline electrolyte. During discharge, cadmium is oxidized and nickel hydroxide is reduced. Because of their reliability and rechargeability, nickel-cadmium cells are used in portable electronic devices. Conventional thermal power plants are not very efficient and are a major source of pollution. In these plants, the chemical energy released from burning fossil fuels is first converted into heat, then into mechanical energy by turbines, and finally into electrical energy. Each step leads to energy loss. In contrast, galvanic cells convert chemical energy directly into electrical energy and therefore are much more efficient. Building on this idea, scientists have developed special galvanic cells in which fuel is supplied continuously and products are removed continuously. These cells are known as fuel cells. Fuel cells are designed to convert the energy of combustion of fuels like hydrogen, methane or methanol directly into electrical energy. One of the most successful and widely studied fuel cells is the hydrogen-oxygen fuel cell. It was famously used in the Apollo space missions, where the water produced during the reaction was collected and used as drinking water for astronauts. In this fuel cell, hydrogen and oxygen gases are passed through porous carbon electrodes dipped in a concentrated sodium hydroxide solution. To speed up the reactions, catalysts such as finely divided platinum or palladium are used. At the anode, hydrogen reacts with hydroxide ions to produce water and electrons. These electrons travel through the external circuit, generating electricity. At the cathode, oxygen reacts with water and electrons to form hydroxide ions. The overall reaction is simply the combination of hydrogen and oxygen to form water. The key advantage is that this process continues as long as fuel is supplied. Fuel cells operate with an efficiency of around 70%, much higher than thermal power plants, and they are almost pollution-free. Because of these advantages, fuel cells are being actively researched for use in automobiles and future energy systems. Another important application of electrochemistry is the understanding of corrosion. Corrosion is the slow deterioration of metals due to chemical or electrochemical reactions with the environment. Rusting of iron, tarnishing of silver, and the green coating on copper are common examples. Corrosion causes enormous economic loss and can lead to serious accidents such as bridge failures or structural collapse. That brings us to the end of this quick revision on electrochemistry. We covered how chemical reactions produce electricity, how cells and batteries work, how electrode potentials and the Nernst equation guide predictions, and how these ideas extend to fuel cells and corrosion. If these concepts are clear, most numerical problems and theory-based questions from this chapter become far easier to handle. Use this video as a last-minute refresher or a foundation before deeper practice. Revise the formulas, understand the logic behind each process, and electrochemistry will feel far more systematic than memorized. Keep revising with clarity, and I'll see you in the next chapter. Until then, it's RJK signing off.